All right, so now that we've had a brief foray into the world of polar coordinates and polar graphs, it's time for some calculus. All right, and we're going to start with differentiation, all right, in polar. So up until this point, right, we have hopefully seen that all of our polar graphs are functions of parameters r and theta, right? Really, polar equations are a set of parametric equations, right? They are defined like this, right, with the equations that we found when we discuss converting between rectangular and polar coordinates, right? That's a set of parametric equations right there. So this happens to be a function of two parameters, r and theta. Okay, right? But the equations that we have been seeing when we look at polar graphs all involve r as a function of theta. For example, we saw, some circles, right? The graphs of circles that, were like r equals some number times cosine theta or sine theta, right? We saw some lemniscates or cardioids or, whatever, maybe like this, right? And then we saw some pretty rose curves, maybe, cosine 4 theta, right? And I'm sorry, of course, I forgot the main point here was that we have r equals in front of all of these, right? So in each of these cases, we have r as a function of theta, right? So in each of these cases, your radius is determined by what theta is. In other words, radius is a function of your angle. And so now why is this important or helpful? Well, polar equations, again, are just parametric equations, and we know how to do differentiation for a set of parametric equations, right? But what becomes difficult, right, and hopefully maybe you can see this, is that when we look at our set of parametric equations up here, all right, you know what, even before we do that, keeping that in mind, let's just remind ourselves, all right, what differentiation for parametric equations looks like. All right, so for a set of parametric equations, right, we found that dy dx was given by dy dt over dx dt. Now, all right, in this case, right, for polar graphs, right, x is not, x and y, they're not a function of t, they're a function of, r and theta, right? Our parameter is not t anymore. So really, we would be looking at dy d theta over dx d theta. All right? Okay, and so let's do that. Let's get the derivatives of, x equals r cosine theta and y equals r sine theta and get dy dx, for a polar graph. Well, why is that a problem? Hopefully, right, you could see that, well, x is a function of two variables, right? You've got r and theta, and the same thing for y. And r is not a constant, right? Your radius changes based on what your angle is. So we've got two variables here. But in order to use this definition of slope of the tangent line for parametric equations, we need to get it down to a function of one variable. And that's where this is going to come in handy, right? Because all right, we can now rewrite this, right? We can now rewrite this as x equals, well, you know what? Let's not call it r, right? If the radius is determined by what my angle is, let me call r f of theta, right? Just say, you know what? Hey, I know my radius is a function of theta. Fantastic. And then same thing for y. And so now we can do this, right? We can figure out dx d theta and dy d theta because we've reduced x and y to a function of a single variable. theta. All right, so scoot down here a little bit. All right, and remember, ultimately, this is what we're going for, right? Because polar is really just a specific case of a set of parametric equations. We want dy d theta over dx d theta. So let's go ahead and get it. All right, so in this case, all right, dy d theta is, now hopefully, we realize that we actually need product rule here, right? F of theta, cosine theta, that's two functions of our variable theta being multiplied together. We need product rule, all right? Luckily, it's just product rule, not quotient rule, okay? So, all right, product rule for dy d theta. So product rule would be derivative of my first function times my second plus the derivative of my second times my first function. So all I did was differentiate y with respect to theta using product rule. And I'm going to do the same thing for x. All right, so now product rule for our x component, right? Derivative of the first times the second plus the derivative of the second, so that's a negative sign now, times the first. So that now when we bring these together, we get that dy dx, right? We know that that should be dy d theta over dx d theta. All right, and so let's write that with the expansion that we have here. So dy d theta is going to be f prime of theta sine theta plus f of theta cosine theta over dx d theta. And so, hopefully maybe you're seeing there's some structural corrections that I'm making here just for the sake of elegance. Right, but that's the idea. All right, and that is kind of one of those things that you just have to know. But the good news is it comes right from the parametric, definition of the derivative and, polar coordinates. And you can always go back and figure this out. The only disadvantage is that doing that takes time. All right, so let's put this in here. All right, that's enough. That's enough to put it in the books. All right, so dy dx is, all right, got your f prime sine theta. Okay. And then, of course, this is, provided that whatever you get for your dx d theta does not equal 0. So let's go ahead and put this idea into use. Okay, so this problem in example 1 asks us to locate the horizontal and vertical tangent lines of the following polar graph, r equals 2 cosine theta. Right, so although our discussion of the different types of polar graphs was a little brief, all right, maybe you recognize this as the graph of a circle, right? It is r as a function of cosine theta, so it's going to be oriented sort of horizontally. It's going to be centered on the x-axis, right, on the positive side of the x-axis because it's a positive 2 cosine theta. And we had talked about how that a value corresponds with the diameter of the circle. So we can sort of piece together that our circle, should sort of look like this. Okay, and so that, there would be its center at 1, and this would be at 2. Okay, so let's mark these points where the tangent lines would be. We'll start with horizontal. So where do we expect that we would have horizontal tangent lines. All right, well, hopefully, start to see right up here, right? And potentially at the bottom as well. And so really all we need to figure out, right, is at what value of theta does that happen? Okay, so in order to do this, right, analytically, all right, well, we'll need to, say, okay, so, all right, if we have horizontal tangent lines, what does that mean? Right, well, if your tangent line is horizontal, that means that your slope is 0. So in other words, the slope of the tangent line, dy dx, is equal to 0, right? And when will that happen? Well, when our numerator is equal to 0, right? So let's just remember, all right, that dy dx, right, for any set, for any polar graph will be given by f prime of theta sine theta plus f of theta cosine theta over all of this. And so if we need this set equal to 0, really it's just going to narrow down to our numerator equal to 0. Ultimately, we will have to check and make sure that, at any of these places, our denominator isn't also equal to 0, but also we look at the circle, we expect this to happen in 2 distinct locations, so that if we get more than 2 results, we might have to go back and say, okay, which one of these is a red herring? Okay, so at the end of the day, all right, we're really looking at, or I should really say from here, we go to, okay, f prime of theta sine theta plus f of theta cosine theta should be equal to 0. And so now we need to remember, all right, what was our function of theta? Oh, right, f of theta, that's r. All right, so I'm actually going to fill this in here first, right? R is 2 cosine theta, right? That's r right there. So let's put that in. R was 2 cosine theta. And then that's times cosine theta. So then, what is f prime? Well, that would be negative 2 sine theta. Okay, and that should all work out to be equal to 0. So really what we have is negative 2 sine squared theta plus 2 cosine squared theta equals 0. I can divide out the 2, right? So that I have negative sine squared theta plus cosine squared theta equals 0. And if I rearrange this, I actually get a nice convenient little trig identity, right? That cosine squared theta minus sine squared theta, that's equal to cosine 2 theta, right? So from here to here, this is just a double angle identity. This is equivalent to cosine 2 theta equals 0. How did I know I wanted to do that? Well, I would rather be solving something with one, trigonometric function than 2, although I'm sure there are other ways that you could go about this. All right, so when will cosine be 0? Well, that's going to happen at pi over 2 and 3 pi over 2. So then it must be the case that 2 theta works out to be pi over 2, right? So that, we're actually taking the cosine of pi over 2 and getting 0, right? Or it has to be the case that the stuff inside the trig function works out to be 3 pi over 2. So this gives us 2 solutions, that theta equals pi over 4, or theta equals 3 pi over 4. So we only got 2. We are expecting 2. So everything's probably on the up and up. All right, now, if you were asked to find the coordinates of that point, honestly, that would be a little trivial because we can sort of see from the graph, that if we're at the bottom of the circle, that's probably the point 1, -1, because the circle has a radius of 1, right? But if it weren't so obvious, right, you would need to plug that value of theta back into, x equals, r cosine theta, et cetera, to get your actual rectangular coordinates. All right, so that answers the question of where are the tangent lines horizontal. And so then we just need to answer the question of where are those tangent lines vertical. Ooh, I know I'm taking you all over here, but let's go back to the picture and eyeball where this should happen. Okay, so we sort of expect that it would be here and here. So again, we are expecting 2 answers. Okay, and then we have to sort of think, okay, well, when would the tangent line be vertical? What would that mean, algebraically, analytically? Well, that would mean that our denominator is 0. All right, so, for vertical tangent lines, right, we're pretty sure, right, that would mean that my slope would have to be undefined, which means that for, dy d theta over dx d theta, right, that dx d theta would have to equal 0. Okay? And so dx d theta, all right, well, actually, we can just sort of remind ourselves that x is given by r cosine theta in general, right, for any. And so here's one more good problem that's really going to just ensure that you understand, how polar graphs work and how the differentiation works. So again, notice it's the same curve, r equals 2 cosine theta. So it's the same circle with the same orientation. All right, mine's a bit of a wobbly circle. Apparently I've had too much coffee. All right, but it is what it is. All right, so give the equation of the line tangent to the graph of r equals 2 cosine theta at the point where theta equals pi over 3. All right, so look, this is the equation of a tangent line. It's a line. It's got to look like this, right? It's got to have the equation of a line. So there's a few things that we're going to have to fill in here, right? We're going to need my x and y coordinate at the point where theta equals pi over 3, and we are going to need the slope at that point as well. If we can fill in all of those things, we will be in good shape. All right, so let's figure out where we are when theta equals pi over 3. Again, I think this will just be good because we can sort of have a sense of what the slope should be. All right, so, when theta, whoops, that's a highlighter. All right, so when theta equals pi over 3, we have r equal to 2 times the cosine of pi over 3, which is 2 times, let's see, cosine of pi over 3 is 1/2. So that's 1. So that gives me the set of polar coordinates 1 pi over 3. All right, so that tells me, all right, go out to a radius of 1, which is here, we know that, and then rotate pi over 3. All right, so maybe, sort of like this radial line represents pi over 3. All right, so maybe roughly, so 1, and then rotate to there. So we're looking at right here, okay? So that now if we want to draw the tangent line there, all right, the line tangent to that point would be something to this tune. So we are looking for a line with a positive slope, all right? And so kind of the way that, you want to go about it is up to you. You could try to get a slope first, or you could try to find your x and y coordinates there first. That is very much up to you. All right. So let's get the point first. Why not? All right. So we know that your x and y coordinates, right, are given by, right, x equals r cosine theta, y equals r sine theta. Right, now technically, right, if we were to plug in our function into this, we would have 2 cosine theta, and 2 sine theta, or 2 cosine theta, sine theta. Right, but ultimately, we know, right, we already know the radius, and we can do the cosine of our angle at the point, right? At the point where theta is pi over 3, right? So both of these, evaluated at the point where theta is equal to pi over 3, right? Well, we know something about that. We know that at the point when theta is equal to pi over 3, our radius is 1. And then we need the cosine of pi over 3, right? And again, for y, our radius is 1, and then we need the sine of pi over 3. All right, so really, I should have 2 sets of equal signs here. All right, or you can go back and you can just plug theta, into each of these. It should work out the same. All right, so cosine of pi over 3 is 1/2, and the sine of pi over 3 is root 3 over 2. Right, so hopefully we believe that that black point corresponds to the rectangular coordinates 1/2 root 3 over 2. And so now we can go ahead and plug these points back into the equation of the tangent line, right? So that we have, y minus, so y was root 3 over 2 equals, we still need m, so we're going to hold off on that, x minus 1/2. So that's what we've got so far. So now we just need our slope, all right? And so this is where our derivative comes in, all right? So we basically need dy dx evaluated at the point when theta equals pi over 3. But first we need dy dx, all right? So that is going to be dy d theta over dx d theta. Now, I'm going to be taking a shortcut here because this is the same function that we worked with on the previous page. Guess what? We know dy d theta and we know dx d theta. And so, if you want to go ahead and just find dy d theta and dx d theta, again, you certainly can. But on the previous page, we had found that dy d theta was actually, I believe it was 2 cosine squared theta minus 2 sine squared theta. Okay? You might have to look back and just convince yourself that that was actually true. All right? And we had found that dx d theta was, it was a negative 4 sine theta cosine theta. All right, now we can just plug in, right, theta equals pi over 3 right now, but this is a little, that's a lot of work. That's too many opportunities to make mistakes, if you ask me. So I'm going to collapse this a little bit, right? This is 2 cosine squared theta minus sine squared theta. And this is negative 2 times 2 sine theta cosine theta down here. So I'm going to go ahead and use my double angle identities again, just like I did on the previous page. All right, so cosine squared theta minus sine squared theta is cosine of 2 theta. And then 2 times sine theta cosine theta is a sine 2 theta. So at the end of the day, the 2 over the negative 2, that gives me a negative 1. All right, and cosine over sine is, that's actually going to be cotangent. Or I could just leave it. I could just leave it as negative, I don't know. Well, let's just do negative cotangent 2 theta. I'm feeling lazy today. So now we just need that evaluated at the point where theta is equal to pi over 3. All right, so this is going to be the negative cotangent of 2 pi over 3. Okay. Well, let's see. The tangent of 2 pi over 3 is negative root 3. So let's see. Cotangent is negative 1 over root 3. So negative cotangent is 1 over root 3. Okay, might want to double check me on that, but I'm sticking with it. So our slope is 1 over root 3. All right, so what I would do at this point is take this, all right, graph your circle on Desmos, graph the equation of the tangent line, and confirm that it goes through the point, that has the polar coordinates 1 comma pi over 3. All right, it should all add up. All right, and now I know it looks like a lot of work that went through here, but we were able to take some shortcuts because of work we had done on the previous page, and everything really comes back to these definitions, right? That if you're in polar coordinates, x is our cosine theta, y is our sine theta, and that your derivative is given thusly. If you can work with that, you can find a way every single time.